In section 5.2, we're going to talk about finding volumes of solid of revolutions. We can use three methods in this section: method of disks, washers, and cross sections. So the idea of the section is such that a region in a plane is going to be revolved or rotated about a line in the plane, and the resulting solid is what we call the solid of revolution. That means the rotation, and it is generated by the region that's being revolved. Okay, now we're talking about one complete, not partial rotation or revolution. This region is going to be bounded, and it's typically revolved about either the x-axis or the y-axis, and it could also be revolved about a line. So that's what we're going to take a look at. So in our first diagram that we have here, we're looking at the region given by area under the function f of x. And the region is being revolved about the x-axis. So this would be the axis of rotation about the x-axis. The arrow that goes like this means the rotation is in that direction. It doesn't make a difference which direction you rotate, you can rotate in that direction. That means clockwise or counterclockwise. As long as it's a complete rotation, it doesn't matter. Okay, so the region, of course, is this region that's being revolved about the x-axis. Now to the right, you actually have the resulting solid. That's what this is going to look like. And what we're interested in is the volume. This is a hollow solid. I guess it could be filled. It doesn't matter for our purpose whether it's filled or hollow. So we're looking at the amount of space inside. That would be the volume of solid that we're seeking. Notice, by the way, that this is not one of your geometric shapes. So for example, we don't have like a cylinder, or we don't have a pyramid, we don't have a sphere. So these are regions or volumes that are defined by a function. Now how are we going to actually find this volume? There are different ways we can do it. The method of our focus here that we are looking at is called the disk method. So the idea goes like this. Now, initially, this is, of course, the actual solid is what it is to the right. Correct? That is a true solid without any approximation. But one thing we could do is we could partition into subregions. Right, the area under the function from A to B, we can partition it, and then each segment, so each segment of this region would be revolved about the x-axis. Okay, so the region actually, I'm looking at, for instance, let's say this last portion right here, that's just last segment. That segment could be revolved individually about the x-axis. And as it revolves, this is what is going to be the resulting solid. There you go. It's going to be that slice of the total solid. That's what the rotation of that little piece is going to be, that region. Now, we're going to look at actually the rotation of the kth region, which is this region, about the x-axis. And that's what that one is going to look like. So if you revolve it, this is the actual slice, the contribution to the total solid that is due to the kth subinterval. Now we can approximate this the volume of this solid using a disk. And this is the disk that we're going to use. Now if you note, every disk has width and it has height. True? So if I think about, for example, that disk, if I lay it on its side, the thickness of that disk is going to be delta x, right? That's going to be the thickness. And of course, the radius of the disk is given by the function f at x sub k. True? And the way to find the volume of a disk is to find the surface area times thickness. True? So the volume is going for the kth disk is going to be pi r squared times thickness. So that's going to be just for one such disk. And that is what you see down here. Therefore, we can approximate the volume of this solid by looking at a finite sum of these individual disks. And that is what the solid is going to look like. Again, if you look at the actual solid, which accounts for the curvature here, right? The curve of the function, that's going to be approximated by the disk. Now these disks, each will have the radius at the evaluation point, which creates the disk of a given radius. The sum of these individual disks will amount to an approximation of the volume of that solid. And each of these, what's in front of sigma, you have pi r squared times thickness. Remember, delta x is the thickness, while while this quantity in front, pi r squared, will be the area of a base, the area of this disk. That's the surface area of the disk. That's what it's going to be. Okay, and then of course, if we take the limit as n goes to infinity, that means you fit more and more disks through that finite interval from A to B. By shrinking the thickness, then we're going to get the area as the limit of Riemann sum. The volume as the limit of Riemann sum. Therefore, the volume of solid of revolution is given by this expression. And if you recall, going back to our definition of definite integrals, that's precisely how we define the definite integral. Therefore, the volume of that solid of revolution is given by the integral from A to B of pi f of x squared dx. Now, for this work, notice there's no restriction on the function being positive or negative. It doesn't matter. The function, for instance, could be like this, and we revolve this function between two numbers, say a and b, about the x-axis. And when we do, we're still going to get the the solid that we got before, right? It's still going to look something like this. And the reason it doesn't matter whether the function is positive or negative is because also in the integrand you're squaring it. So whether you have positive, negative, you square it, it's going to become positive. The integrand will be positive always, which will result in a positive volume. And there you have it. So again, a region is revolved about the x-axis in this case. And we're going to look at some more general regions where there's actually going to be like a hole in that solid. Right now, the solid, notice, there's nothing inside. I mean, it's one uniform piece, each disk. There is no hole inside of these disks, is what I'm referring to. So we'll look at the case where there are holes, and then we use different methods. So here's an example. For instance, if I want to find the volume of a sphere, now we know the volume of a sphere is what is 4/3 pi r cubed. True. We can actually prove this using the method of dissection. So if you think about the circle center at 0, 0 with radius r, that one, and if you just look at the top half of that circle, you get y equals square root of r squared minus x squared. And if you revolve this region from negative r to r about the x-axis, the resulting solid is going to be sphere. True? So in this case, all you have to do is just use this the formula that we have, right? The limit of integration. Go from negative r to r of pi. R would be square root of r squared minus x squared, pi r squared times thickness. And if you evaluate this, which we can, the volume is going to be 4/3 pi r cubed. You can try it. You can try and see that indeed that's what is going to happen. But notice how the solid of revolution is generated. So we're looking at a typical rectangle of width delta x rotated, giving us the solid of revolution in this case. Okay, now let's take a look at another way to revolve this region. This time we're going to revolve it about the y-axis. So the rotation is taking place with respect to the y-axis. And in such instance, we need to have x expressed as a function of y. And we're going to use horizontal rectangles here, or really horizontal disks they become once you revolve them. Each of these rectangles, to begin with, have a thickness delta y, or dy call it. And once they are rotated, that's how they generate this disk of thickness. That's going to be dy, right? As number of rectangles here increases, dy and delta y approach the same number, right? Delta y is approximately equal to dy. And of course, the radius is given by distance from the y-axis to the curve, and that is what gy is. So that distance right there, that's what x is, the radius of a disk. Okay, and of course the rotation takes place and you get this interesting solid. Okay, so if the rotation is about the y-axis, therefore we need to adjust it. The adjustment is limits of integration now are on the y-axis. True, so they go from c to d. And of course the radius now, instead of y, is now x squared. Look at the radius here before. The radius, remember, f of x means y. True. So with rotation with respect to the x-axis, this integrand becomes like pi x squared dx. True. Or I'm sorry, pi y, because f of x is y. Pi y squared dx, and y is stated as a function of x. And down here you have pi x squared dy. Now when we do this, it's important that x here, x is stated in terms of y, because the variable of integration is y, not x. Okay, and there you have this one. And let's see, next method, we'll look at some exercises in a few minutes. Let's look at this next method. For this next method, it helps when they're solid of rotation or revolution. Notice it's actually inside there is a hole inside. So when there is a hole inside of the solid, we use this other method called Washer's method. Okay, so with washer, what happens is you have an outside and then you have an inside. So there's your washer of fixed thickness, right? The thickness, called it delta x. And we're looking at what's on the outside here. So that's what a typical washer looks like, right? So this is like delta x sub k, the kth washer, which is this one. All right, this thickness is delta x sub k. Now, how do I get the actual radius here? So, well, we're going to have an outside radius, and then we're going to have an inside radius. True? The outside radius is given by the outside function. That's the outside function. And the inside radius is given by the inside function. All right, and in this case, f is the outside, g is the inside function. And again, you can see as you revolve this region or about the x-axis, the kind of solid we're going to get. So keep in mind, you use washers for solids that have holes in them. And in fact, you can use discs for these also. If you use disc, you need to use outside discs. So there you go. If I use discs instead of washers for this particular example, my volume is going to be for the outside. So I'm thinking this region first, which is solid, no hole inside. That's based on the outside function. Okay, so that's going to be pi r squared. Okay, so the volume is going to be pi outside squared minus pi radius inside squared. And once you factor pi, you get r outside squared minus r inside squared. True? And that's what this is. So again, washers are special cases of disks. So you have outside disk, and then you take out inside disk. You bore a hole inside the solid, and that's how you get the final solid of revolution. And there it is. Okay. Here's an example with specific functions as you revolve a typical cross section here. Not cross section maybe, but typical rectangle of a cross section. You revolve it, you're going to get this washer of thickness dx, and again you get this kind of looks like a parabolic region, right? The parabolic, there you go. That would be if that was just a solid without the lower function. Okay. And then once you throw in the inside function, that's how you get this solid of revolution. Which again, the inside here, this part is hollow. This is hollow inside. Okay. So anytime there is a hollow space inside the solid, we're going to use washers. Now we could actually revolve about an axis. In this case, the rotation is done about a line. Usually we revolve about x or y axis, but those are lines too, right? So for example, when you revolve about the x-axis, you're revolving about y equals 0. True? Now, when you look at y equal to 2, it's the same principle. So this is the effective axis of rotation, y equal 2. So we still do the same thing. You go outside radius, right? This would be on the outside, and what's inside is here. That's inside. And so we're going to get the following drawing, this diagram to the right. Okay. Now, the outside radius, again, the outside radius is the distance from the center out to the outside function, which is, remember, y equal x. That's what this is. And for this one, we're going to get, let's see, outside. So the distance here, as you can see, this distance is going to be 2 minus x, right? Because the y value, the height of this point is y. This is y, which is equal to x. And that's how we get 2 minus x. That's what it is in here. So that's the distance to the, this is outside radius. The inside radius is the distance from the center to this square root. There you go. That's the effective inside radius. Remember, from here all the way down here to the x-axis is 2 units. And from here on the x-axis, a point on the x-axis to the curve, this is going to be the y, which is given by square root of x. True? Therefore, the inside radius is going to be 2 minus square root of x for that reason. Okay, and once you set up these, you can then set up the integral and then evaluate the integral. Okay, we need the outside-inside radii because that's what's in the integrand. Those determine directly what the integrand is. And be careful here, notice f must be greater than g. Has to be greater than g, otherwise we're going to get negative volume. Okay, which is not acceptable. Here's another instance where the rotation is actually done about the y-axis now. So the same principle, so the washers fit in this direction, in a horizontal direction, right? Notice here the washers are vertical. Now you have horizontal washers when the rotation is about the y-axis. And as they fit the solid, thickness is dy, the radius inside, and then this would be the outside radius, right? Remember, those are going to be functions of x now for rotation with respect to the y-axis. And there you go, if you're interested in specifics of this one. So you have outside. Remember, outside is y equal x. This is the outside radius. So you're going to square it. There, that gets squared. And then inside is given by this equation. When we have y equal root x, that means x equals y squared. Because the variable of integral is dy, we need to write x as a function of y. And then you get y to the fourth because you're squaring the y squared. Okay. And then the details of the integral is, the rest is easy. The integration portion is pretty easy. And you get your desired outcome here. And in this work, notice we don't use calculators. We like exact values without calculators. Okay, so, and that's about it. That's just methods of disks and washers for both rotation about the x and about the y-axis. Now, the last method here, which doesn't involve rotation. In this last method for this section, we're talking about the method of cross sections. Using method of cross sections, we actually construct or build a solid. You do not revolve or rotate about anything. You build a solid from scratch. Okay, so in this case, let's say here we have a pontoon. That's what this is. This is a pontoon. Looks like a submarine, right? And what the author's done is taken a look at the cross section of that pontoon. That's some k, distance k away from the origin, from the zero. Okay. Now, this is what the cross section actually looks like. Okay, of that at x. This is what a slice, if you will. If you slice that pontoon, like you slice a bread, that's what the cross section will look like. Now, imagine if we could slice this pontoon into finite number of pieces. So you slide like that. Of course, these slices are vertical, right? As you can see here. So you just cut them here. So the cross section is perpendicular to the x-axis in this case. Okay, and then what he's doing is actually looking at the cross section. So notice this portion of it is right here, and then the curved portion is estimated by a straight line, and these are the slants right here. Okay, so that would be an approximation of a cross section of a pontoon. The volume of that cross section that you're looking at, this volume, is given by the surface area times thickness, right? So let's say you're slicing it right here. Okay, and that's what this looks like. So if you multiply the area of the cross section times thickness, then that will give you the volume of that slice. And of course, you sum these from 1 to n. Let n go to infinity means you make the slices smaller and smaller and smaller. There you go, like that, until you ultimately get the solid itself. Notice there is no rotation in this case. We're building a solid. So the formula here is, let S be a solid bounded by plane and the planes that are perpendicular to the x-axis at x equal a, x equal b. The a and b give you like right in here. Here's a, here's b. That's the extent of that pontoon. And this is where it starts at A and it ends at B. So it's kind of like your starting and ending point of that solid. And the cross-sectional area of A of x, A is continuous on the closed interval. Then the volume of solid is simply, again, the limit of the Riemann sums. Turns out to be the definite integral of the area of a cross-section times dx, which is thickness. And here you're looking at, again, case, there you go, where you have a solid. The base of the solid seems to be circles, and that's what it is. And then the cross sections that you construct the solid with, these seem to be not equilateral. Yeah, they're isosceles triangles, looks like isosceles, because here they have two equal sides. Okay, if they're equilateral, actually they're equilateral because this is also 2y. Yeah, all three are equal. So you have equilateral triangles that are constructed here, there. So this is how the solid's going to be done there. Okay, and once it's constructed, then the key here is to be able to find area as a function of x. That's the key. Once you have that, then the actual integral is easy. You multiply that times thickness. So the key here is, how do I determine the area as a function of x? Okay, so let's take a look at an example here. This is in your book. In this example, we want to find the volume of this pyramid. Now, if you look at the base of this pyramid, the base is a square, right? The bases are squared, and they are perpendicular to the y-axis, actually, right? Each of these is perpendicular to the y-axis because it's parallel to the x-axis. It's perpendicular to the y-axis. Now, we need to find the volume of solid here. So the square, of course, the area of a cross-section, square cross-section, that's going to be that. This is 2x by 2x, right? Now, we need to find the area as a function of y in this case. I know I have area as a function of x. The reason, because here we are perpendicular to the x-axis. If the cross sections are perpendicular to the x-axis, you use ax. So ax, this one, cross sections are perpendicular to the x-axis, and use a as a function of y if the cross sections are perpendicular to the y-axis. Okay, and here we have it. Now, in this case, the key is again in the geometry, of course, of what we're doing here. So if this is one triangle right in here, that's one triangle, and then there is another secondary triangle here, this triangle. So we're looking at those two triangles, and using similar triangles, that's what the author is going to do, is trying to find x as a function of y here. You see that? So using similar triangles, this is the ratio that we get. So in other words, what we're looking at is the ratio of this side in this triangle, small triangle. We're looking at the ratio of the side, which is x, to this side in the larger triangle, which is b over 2. That should equal to, those are the ratio of the sides, right? So that should be equal to the ratio of this side, which is h minus y, to the total side, the entire side of that bigger, there you go, which is h, of the larger triangle, which is h. So that's how he gets this ratio, and from this you get x as a function of y. You multiply both sides by b over 2, and that will do it. Okay, now and once we have that x stated as a function of y, right? and that's what we want because cross sections are perpendicular to the y-axis. Then we can set up the integral, right? The integral limits of integration go from 0 to h because you can start at the base here. This is your first not triangle but square here at 0, right? You started at 0. Then you can kind of build these all the way up to the top, which is h. So the limits of integration go from 0 to h. Okay, and then once we have that a sub y that it was found up here, right? You just plug it in, and then the integration is the easy part here. All right. So there you have it. Let's take a look at some of these exercises now. Okay. Let's see. Let me take a look and see which ones I'm gonna pick to do for the lectures, and then we'll do them. Okay, so here I have these problems circled as I'll go through and work these for you. The latter exercise number 56 has to do with finding volume of solid using cross sections. Okay, so let's begin with exercise number 4. Okay, now in exercise number 4, let me see. The exercise asking us, it says find the volume of solid that is obtained by revolving the region about the indicated axis or line. Now notice in here, because we have horizontal rectangles, so we're going to use dy. And because that's dy, remember the variable of the integration is dy, so you have to have, in this case, a function of y. Therefore, we're going to make the integrand here. You have to have a g of y, right? A function of y. Okay. So let's do number 4. Number 4 that we have y equals 4 minus x squared. True. And if I recall correctly from number 4, let's see, limits of integration go from 0 to 4, and the rotation is about the y-axis. Okay, therefore exercise number 4, the volume is going to be integral from 0 to 4 of pi r squared. Remember, r is x, and dy. Now here I need to solve for x, so x squared would be 4 minus y, therefore x is square root of 4 minus y. Of course you have plus or minus, true, but because we are in the first quadrant here, right, in the first quadrant, x is positive. Here's 0, there's x, right, x is positive, so we're only going to take positive root 4 minus y. That's a 0 to 4 of pi root 4 minus y squared dy, and that makes it pi 0 to 4 of just 4 minus y dy. True, the integral is going to be pi times 4y minus 1/2 y squared from 0 to 4. The lower limit makes it 0 when you plug in 0 for y, right? And the upper limit is just going to be 4 times 4 minus 1/2 times 4 squared. So it's going to be pi, and that's 16 minus 8. So it's going to be 8 pi, right? And there you have it. Let me put them in proper order. That's going to be 8 pi. So there you go. That's the answer to number 4. And then we're going to look at exercise number 8. In exercise number 8, we have a function that is bounded, or the region that is bounded between two functions. The top function is 1/2 x squared plus 2, and the bottom function is x squared. The rotation is about the x-axis. True? The limits of integration, because you have dx, so you look at the x-axis. Limits of integration go from -2 to 2. Okay? And now we're going to put it together in exercise number 8. So problem number 8, the volume is going to be, we can bring pi outside here, by the way, in our formula, because it's a constant, we move it outside the integral. So the outside function is going to be 1/2 x squared plus 2, you square that, right? Minus inside function is x squared, and then dx. Okay, and let's see, now we can simplify this work. Let's expand, and I'm gonna because the region is symmetric. If you go back to number 8, you see the symmetry here about the y-axis, so we can find the volume from 0 to 2 and double that up. So I'm gonna go, actually, instead of pi, make that 2 pi, and then 0 to 2 of, now you square the binomial. This is gonna be first one, 1/4 x to the 4th, plus twice first by second makes it 2x squared, plus last one, minus x to the 4th dx. Okay, and let's see, this will be 2 pi 0 to 2 of, you have 1/4 x to the 4th and whole x to the 4th, that's -3/4 x to the 4th, then plus 2x squared plus 4 dx. So integrating piece by piece, the first one, the integral of x to the 4th is x to the 5 over 5, so that's going to be 3/20th of x to the 5th plus 2x squared, that's going to be x cubed over 3, 2/3 x cubed, right? And the integral of 4 is just 4x, right? That's going to be 4x. Limits of integration run from 0 to 2. Then we plug in the upper and then minus the lower limit. The upper limit 2. So lower limit, again, 0 makes every one of those terms 0, so I won't even try it. First we have 3/20th of 2 to the 5th plus 2/3 2 cubed plus 4 by 2. That's going to be 2 pi times 2 to the 5th. That's, let's see, well, 2 of those 2's of 5 2's cross out with 20, so that's 5. I have 8. True. So it's going to be -24 plus 8 times 2, 16/3 plus 8. The LCD is, let's see, the LCD is, sorry, I dropped the 5 here. That's -24/5. Yeah. The LCD is 15. True. So that's going to be 24 times 3, -72 plus a 15 second fraction, multiply top bottom by 5, that's 80. And the last one, multiply top bottom of 8 times 15, that's 120. Okay, and then combine like terms. So this is going to be what, that's 128. 128 times 2 is 256 pi over 15. There you go. That's going to be the volume of resulting solid of revolution for that one. Okay, so we did number 8. Let's take a look at number 12. Now in number 12 we are revolving about a line here, line y equals 3/2, right? So again, the outside radius is the distance all the way to this function y equal x, right? So remember, from 0 to 3/2, that's already fixed distance, 3/2. So this distance should be less than 3/2, right? So that's going to be what, 3/2 minus y, true? Because we're going with horizontal dy, so everything must be in terms of y. Okay, so it's going to be, again, the distance from here to here is going to be 3/2 minus x, but then x and y are equal, so that's going to be 3/2 minus y. That's that distance. And then this distance is distance from the line to this point. Now that point, this is the x for that lower curve, so it's going to be 3/2 minus x, but then x can be written in terms of y, right? Y is x cubed, so x would be cube root of y, so it's 3/2 minus cube root of y. Okay, that's that distance from this line to this point, to that lower curve again. There, that distance is 3/2 minus cube root of y. Good, and those are the key. So we can do now number 12. Again, rotation, keep in mind, is about this line, y equal 3/2. All right, so the outside function line minus inside function x cubed. Therefore, in number 12, for exercise number 12, I can write the volume is going to be pi. The limits of integration, go back. The limits of integration, because we go along the y, starts here, ends here at 1. See, these would be disks, resulting disks of rotation, can fit from 0 all the way up to 1. All right, along the y-axis. So volume is from 0 to 1 of pi. Outside radius, we said, was 3/2 minus y squared, and inside radius was 3/2 minus cube root of y, true? And then we square that times dy. Okay, so the volume is going to be pi 0 to 1 0 to 1 of, we actually have to raise these to the power. We're going to square them. Okay, so 3/2 squared, that's 9/4, negative twice first by second, that's going to be 3y plus second one squared. That minus, need brackets here, minus 3/2 squared makes it 9/4. Negative twice first by second is 3 times cube root of y is y to a third. We're going to integrate these anyway. I need to write them without the radicals. That's twice first by second, and then plus y to a third squared becomes y to 2/3, and then dy. So this becomes pi, and then we can now combine like terms. The 9/4, those cross out, true? So we have, we get y squared, negative 3y here, true? And negative times negative is positive, plus 3y to a third, and negative y to 2/3 dy. And there we have it. This is going to be pi. Okay, we're ready to integrate now, so let's integrate it. Integral y squared 1/3 y cubed, negative 3/2 y squared plus y to a third plus 1, that would be 4/3. Invert and multiply, we get 3/4. y to 4/3 negative y to 2/3, add 1. 2/3 plus 1 is 5/3, so it's going to be 3/5 y to 5/3, evaluated from 0 to 1. Again, because every term has y in it, the lower term will make it 0. So I'm just going to put in the upper value 1, becomes 1/3 times 1, negative 3/2 plus 9/4, negative 3/5. All of those y to the power of 1, each of those become 1. So the LCD now, 2, 3, 4, and 5. Let's see, that's 6 by 5, 30, but then I have 4, so that's going to be 60, right? The LCD, the lowest common multiple is going to be 60. Now, first fraction, multiply top bottom by 20. Second fraction, multiply top bottom by 30, and so on. 60 by 4, that's going to be 15. 9 times 15, 135. Negative, this would be 12 times 3. Multiply top bottom of 3/5 by 12 to build to the LCD. Okay. And let's see. So the numerator is going to be 155 minus 126 over 60. And 155, take away 126. That's going to be 29 pi over 60. There. So hopefully I did my arithmetic correctly in this one. All right, and that will be the volume of solid of revolution. Now, so far the ones we've done, by the way, notice the graphs were given, so we really need to have the graph. So we cannot do this without graphing. I mean, you could, but it's going to be difficult unless you're really trained and you like to, torture yourself. But when you graph it, it makes it a lot easier because we can see everything from the graph. So let's take a look at now the remainder of these exercises, number 16, 22, and 24, 30. In number 16 here, 13 through 30 exercises read, find the volume of solid generated by revolving the region by the graphs of the equations and or inequalities about the indicated axis. Okay, so let's take a look at starting with number 16. In number 16 we have square root of x minus 1, y 0, x2, and x5. Okay, so let me copy these so it will go faster for us. Hold on. Okay, so in number 16, remember, we need to start by graphing these. So this is my coordinate system. Here's x, y. Square root of x minus 1 is going to be the basic square root that is shifted to the right 1 unit. Now y equals 0, that is the x-axis. True? And that's y equals 0, the x-axis. And x equals 2 is a vertical line at 2. And x equals 5 would be some distance later. X equals 5. Okay, so we have the region identified. This is the region that we're interested in, right there. The region is being revolved about the x-axis. Okay, so here's the x-axis, and that's the rotation. And that's the region R that's being revolved. So for this one, we're going to, let's see, if I, for one thing, let's say if I should use horizontal vertical rectangles. If I use, or discs I should say, if I use discs that go in this direction, dy, And if I revolve these about the x-axis, it's not going to be the same solid as if you revolve disks that go in a vertical direction, right? It's a whole different solid. Okay, therefore because rotation is about the x-axis, I'm going to choose disks that are like that of width dx. Alright, so we're going to use disks in order to do this. Okay, so the volume is going to be equal to pi. The limits of integration, clearly the disks can start at 2 and they end with 5, right? They have to be inside that bounded region. So limits volume 2 to 5 of. Now for this one we're going to, because we have dx, so we're going to have f of x squared dx, and f of x is root x minus 1. So it's pi 2 to 5 root x minus 1. That gives you the radius, by the way. That's the distance from the x-axis to a point here. That's going to be f of x, right? The height is given by f of x, which is root x minus 1 squared dx. And that's going to be square root of x minus 1 squared is just x minus 1 dx. And the integral is going to be pi times 1/2 x squared minus x from 2 to 5. And then you, let's see, plug in the upper lower limit. Let me do these. That's okay. Let me show you. I'm trying to skip some steps so that it doesn't take too long to do these. 1/2 of 5 squared minus 5 minus 1/2 of 2 squared minus 2. And you do this, you should get 15 pi over 2 is what I got. Okay. Let's take a look at number 22. In number 22, first the graph of this thing. Y equals 0, that's the x-axis. X equals 0 is the y-axis in number 22, right? This is x equals 0. And then x equals 3. That's going to be a vertical line at 3. And the rotation is about the y-axis. Now, we don't need to, just between 0, right? This is x equals 0. Between x equals 0 and 3 is all we need this graph for. Now, when x is 0, y is 1. True. That's just plug in 0 in the denominator, you get 1. And as x increases, y, which is 1 over x plus 1 to the 3/2 decreases. It's going to look something like this, right? That's what it's going to be. And at 3, you plug in a 3. 3 plus 1 is 4. 4 to 3/2. That's square root of 4 cubed. That's 2 cubed, or 8. So it's going to be 1/8. This is 3 and 1/8, actually. 8 was just the denominator. 1 over 8 is the actual function value. Okay, and the rotation is about the y-axis. So this time our disks are going to be consistent, so the width of the disk will be dy, because the rotation is about the y. Rotation about the x, we use dx. Rotation about the y, we use dy. So that means the variable of integration is y. So the limits of integration now go from 1/8 to 1. True. Let's see, for number 22, about the y-axis, right? Let me make sure I copy that correct. In number 22, I think it was about the y-axis. Oh, I'm sorry. It's about the x-axis. That's fine. We can set it up for the y-axis, but then the question asks for the x-axis also. So this is actually about, well, I'm going to do it as if it was for the y-axis. Okay. So it's going to be 1/8 to 1, and then the radius of a disk is given by the equation, right? Now for the equation, I need to have x as a function of y. True, that means we need to solve this for x. So I can actually solve this equation then for x. So y is equal x plus 1 to 3 halves. So that means y to 2/3, raise both sides to 2/3 power. And then x would be y to 2/3 minus 1, right? So that's what I have. The outside, inside, the radius is, the disk starts from 0. So it's just going to be pi radius squared, that's y to 2/3 minus 1 squared times thickness. That's if this was about the y-axis. You get a different answer if it's about the x-axis. So then you can finish this off. Now remember, the problem asked for about the x-axis. So let's actually now do what the question has asked us to do. In number 22. So the same graph that I had before, right? My graph doesn't change. It's just the rotation about which axis changed to the x-axis now. Here's 1, and this point is now 3. The disks, and by the way, the disks now go in this direction, right? The vertical disks. So you get actually a solid, you get something that looks like this. True. You're going to get a solid that looks like that. This would be the x-axis. That's the solid. A whole different solid than the one above it. With the one above, with this one, if we had pursued that, our solid would look different, right? Our solid would look like this, right? Look at that solid, look at the one below. There are two different solids. Okay, let's set up our integral. Our integral is going to be, the volume is pi from 0 to 3 of r, which is f of x. F of x is y squared dx. Now, that's going to be pi from 0 to 3 of, the equation was 1 over x plus 1 to 3 halves. And then we square it, right? 1 over x plus 1 to 3 halves squared times dx. Now when we square the function, we're just going to get x plus 1 cubed, right? So it's going to be, and it's 1 over x plus 1 cubed dx, and then invert, we get pi 0 to 3 of x plus 1 to negative 3 dx. Okay, and this would be pi. Let's see, the integral now. If I let u be x plus 1, du is dx, right? So the integral as an indefinite integral is that of u to negative 3 du. That's going to be negative 3 plus 1 is negative 2, u to negative 2 over negative 2 plus a constant, right? So the indefinite integral is going to be negative 1/2 times x plus 1 to negative 2. Okay, so that's what I'm going to write. That's negative 1/2 times x plus 1 to negative 2 evaluated from 0 to 3. That's negative pi over 2. The upper limit, 3, makes this 4 to negative 2. The lower limit, 0, makes it 1 to negative 2. Now 4 to negative 2, that's going to be what, 1/16 minus 1, which is negative 15/16. Negative times negative, this makes positive. So the answer is going to be 15 pi over 32. And that's what that is. Again, if you do the one I set it up incorrectly, you get a whole different answer. All right, that's number 22. Let me grab the next one. Okay, so in number 24, let's graph this one. Now, for y equals sine x again, let me do that in a moment. But y equals 0, that's just the x-axis, right? Y equals 0 is the x-axis. So this is y equals 0. And then x less than or equal pi over 2, call this pi over 2. Right, x equal pi over 2. Less than or equal means everything to the left, right, of that. And then let's see, square root of sine x. Well, square root of, because the radicand must be positive, so we know sine x has to be positive, right? That's the implied domain, right? Implied domain of the radical. All right, now sine, because we are in the first quadrant, well, sine, the sine function is going to go like this, right? Well, this part of it we don't need because it's above pi over 2. Therefore, the only part of sine that we need is this part. And although you take the square root of it, right, so it's really square root of, I don't know, w. The general square root function looks like this. It's just the radicand happens to be sine, but it's positive. So it's going to behave like the general square root function, the graph is. All right, and that's all we need. This is the region that's bounded. True? Now the rotation is about the x-axis, so that means the disks will have width dx, right? They have to be consistent with the axis of rotation. With x you go dx, about the y-axis you use dy. And there we go. As we revolve this, it's going to be pretty easy to set up now, right? The volume is going to be pi, limits of integration 0 to pi over 2 of the general form is y squared dx, or f of x squared dx. That's just the general form. So that's 0 to pi over 2, and then y is the square root of sine x in this case. That gives you, again, each disk, see, the disk will have different heights. The height is given by root sine x. That's why we allow it to be different. Squared dx. And square root of sine x squared is just sine x. That's the integral from 0 to pi over 2 of sine x dx. And the integral of sine is going to be negative cosine, right? And so that's negative pi cos x 0 to pi over 2. So be careful for this one. Usually for polynomials, remember, we use 0 for x, so we don't plug in for x. Cosine of 0 is not 0, so you actually have to plug in. Cosine pi over 2 is 0, minus cosine 0 is 1, not 0. So that's going to be pi. The whole thing said and done will be pi. The volume of solid of revolution will be pi. That's number 24. Let's take a look at the next one. All right, so this is number 30 now. So if I graph this thing, the first one we recognize as the equation of a circle. In fact, the unit circle, right? Center at 0, 0, radius 1. So that one is going to look something like this, the unit circle. And then next we have a sideways parabola, 3/2 x, right? So that's going to be more like so. That's your 3/2 x, the parabola. Now we are told the smaller region, there are actually two regions here formed. This is one region, and the other region is this region, right? We're told the smaller of the two regions is what they're looking for, what they're seeking. So I'm going to remove the red. True. And we want the area of that green region. So we're going to use symmetry, right? We're going to use symmetry, and the rotation is about the y-axis in this case, right? So remember, for if the rotation is about the y-axis, then our rectangles are going to be horizontal rectangles with dy. that's how we're going to align our disks, and then the disks will revolve about the y-axis. Okay, now therefore we need to write x as a function of y. The formula is pi gy squared, pi x squared dy from c to d, right? That's what we're about to do. The limits of integration, by the way, in this case, because we're taking advantage of the symmetry, right? Because we don't want to go over the region twice. Okay, so let's see how we're going to set this one up. All right, again, this is what we want to do. See that there is an upper and there is a lower portion. So I would like to go volume is 2 times. Now 2 times, I'm just going to look at the upper region. That's going to go from 0 to the point of intersection of the parabola and the circle. So let's find that point of intersection, the parabola and the circle. For the circle, we have y squared is 1 minus x squared. True. For the parabola, we have y squared equal 3/2 x. Well, if we set the y's equal to each other, because at the point of intersection the x and y's are the same, right? So I'm just going to plug in for y squared 3/2 squared into the first equation. Okay, and then we should be able to solve for x. So I have plug in for y squared 3/2 x equal 1 minus x squared. That means x squared, bring x squared over, in fact bring everything over to the left. You get x squared plus 3/2 x minus 1 equals 0. Multiply the entire entire equation by 2 to get rid of fractions. We get 2x squared, 3x minus 2 equals 0. And at this point, we can actually use quadratic formula, right, to solve for x. Negative b plus or minus b squared minus 4ac divided by 2a, which is 2 by 2. It's negative 3 plus or minus square root of. The radicand is going to be 16 and 9, 25 divided by 4. So that's negative, let's see, making sure I set them up correctly here. Yeah. So it's going to be negative 3 plus or minus 5/4. That will give us the x component of the points of intersection. So one point of intersection, called it x1, will be negative 3 plus 5/2, which is 1/2. The other point of intersection, x2, is going to be negative 3 minus 5, negative 8, negative 2, right? So 2/4 minus 2. Okay, now let's see, for this one, x negative 2, well, x equals 1/2 is the one that we actually use here, right? This one. This other equation, this one will not work. And that's not x over 2, I meant x sub 2. Okay. Negative 2, and this negative 2 actually, this one we cross out. This negative 2 is not in domain of circle. It's a unit circle that runs from negative 1 to 1. So you're going to toss that one out. So the only point of intersection is when x is 1/2. Okay, so when x is 1/2, add x equals 1/2. What is y going to be? Well, we can plug in, remember, y squared plus x squared is 1. We can go to equation of a circle, so that's y squared equals 1 minus x squared. 1 minus 1/4 is 3/4. So y would be root 3 over 2, plus minus root 3 over 2. And those are the 2 points of intersection. There you go. One of them is here. This is 1/2 and negative root 3 over 2. The other one is positive 1/2 and root 3 over 2. That's this one. 1/2 and root 3 divided by 2. Okay, that's the one we actually want. The limits of integration are determined. The volume would be pi. Oh, I'm going to go twice. 2 times pi from 0 to 1 to square root of 3 over 2. Okay, that one of let's see, the function on the right side is going to be 1 minus y squared, right? It's the circle. To the left is parabola, which is 2/3 y squared. Squared for the, and then we're gonna square each of those, right? That squared, and this one squared, and then dy. Okay, and there we have it. Now, let's see. So for this one, yeah, we used washers actually on this one. Yeah, we use washers. Remember, because there's going to be a hole in the solid, so we use washers. This would be outside radius minus inside radius. That's what we did. And oh, actually, hold on. There is no square on the first one, and here's why. X is square root of 1 minus y squared for the circle, so this would be the outside radius. Okay, that's gonna be 1 minus, yeah, and then when I square it, x squared becomes 1 minus y squared, which is outside radius squared, right? And same thing for the parabola. The parabola had the equation y squared equal 3/2 x, right? Or x from here, multiply both sides by 2/3, you get x equals 2/3 y squared. And that one gets squared. 2/3 y squared squared. That looks right. This equals to 2 pi 0 to root 3 over 2. 1 minus y squared, we're going to keep that negative. 2/3 squared is going to be 4/9 y to the 4th, and then dy. Okay, so this is going to be 2 pi. The integral of y, that's of 1, is just going to be y. Y squared becomes 1/3 y cubed, and this other one is going to be y to the 5th over 5 negative 4 45ths y to the 5th, and the limits go from 0 to root 3 over 2. Now when we actually plug in the numbers, okay, that's root 3 over 2 minus 1/3 root 3 over 2 to the 3rd power negative 4 45ths root 3 over 2 to the 5th power. Okay, now root 3 cubed, that's going to be 3 root 3, right? And root 3 to the 5th is going to be, it's like root 3, right? Remember how this goes? You can multiply these together 5 times. For every pair you just get 3, so that's going to be 9 root 3. Okay, I needed to simplify. It's going to be 2 pi root 3 over 2 minus 2 cubed is 8 times 3 24, root 3 cubed is 3 root 3 minus 4 45ths root 3 over 2 to the 5th, that's going to be 9 root 3 divided by 2 to the 5th is 32. Okay, and then I can let me simplify this and then put the answer for you. Alright, so I went ahead and simplified this fraction. The LCD turns out to be 1440. So I build the first fraction, multiply top bottom by 720. The middle one, multiplying top bottom of that one by 60. And the last one, of course, its denominator is the LCD, so I didn't multiply by anything, just 4 times 9 in the numerator. Then combine like terms, and hopefully I got the right answer. And there you have it. So this is the answer to now exercise number 30. Okay, let's take a look at exercise number 38. Okay, so here's number 38. In number 38, we want to find again the solid of revolution, this time generated by revolving the region bounded by the graphs of the equations about the indicated line. So we are actually revolving about a line, not the x or y axis. The line is x equals 2. So I went ahead and graphed these. Again, these are simple graphs. Y equal x squared is a parabola, and y squared equal 8x is also a sideways parabola, that one. The point of intersection of these two ends up being 2, and you can find that easily if you set the y's equal to each other. So remember, y equal x squared and y squared equal 8x. If you solve that system of equation, plug in for y and x squared, so you get x squared squared equals 8x, true. And you can also square x squared becomes x to the 4th minus 8x equals 0. Factor the x, we get x cubed minus 8 is 0. So that means by 0 factor principle, x is 0 or x cubed minus 8 may be 0, which means x cubed is 8 or x is cube root of 8 or 2. And there we have it. So the points of intersection are at 0 and 2. Now, we're going to revolve this about a line x equal to this vertical line. And remember, whatever your rotation is, we're rotating about the vertical, so we're going to use horizontal, in this case, washers. If there is a gap, if there is a hole right in here, that's the inside. If there's an empty space inside the region, we use washers. Okay, and remember, washers are like discs that are hollow. So we use outside disk, full disk, and we take out, subtract out the inside disk, which creates a hollow disk, which we call a washer. Okay, now the distance from 0 to the vertical line is 2. What I'm trying to find here is actually this distance from here to this point. Well, that point, it's going to be x units away from the y-axis, according x given by the sideways parabola. So it's going to be 2, right? It's going to be 2, take away the x. So we can actually determine the distance to the axis of rotation. Therefore, the outside, let me just put our outside, is going to be 2 minus x, but x for the sideways parabola. And I found those here. For the sideways parabola, x is 1/8 y squared. So that's 2 minus an 8 y squared. That's going to be the outside radius. Okay. Now, the inside radius is going to be 2, again, minus, let me use this one, like that. Right, we're looking at this portion now, this segment right here. We want to find this distance from 2 to there, right? So that distance is the distance from the y-axis to the basic parabola. This is y equal x squared, or x equals root y. True, so that distance is root y. That's how far that is. So if I do 2 minus root y, I get the desired distance. Okay, and that's what we want. That's going to be the inside radius. Our inside is 2 minus square root of y. And once we figure those out, then pretty much the rest is easy. Now, the limits of integration, these washers can go from 0 up to, when x is 2 squared 4, up to 4, right? That's what those are. And that determines the limits of integration. So using washers, we have the volume is pi 0 to 4 of the outside, right, the radius, which is 2 minus 1/8 y squared minus inside radius is 2 minus square root of y squared. And there we have it. Now the volume is going to be pi 0 to 4. Square the binomial, I get 4 minus 2 times 2 4/8, that's 1/2 y squared, plus a 1/64 y to the 4th, minus the square of the binomial, which is 4 minus twice first by second, 4 root y, plus root y squared is just y. And there is dy. Okay, now let's simplify this thing. 0, I put the pi on the outside. Very, very normal routine. We pull the constant out. Okay, let's see. Now in this work we have -4 and 4. That's good. Those add to 0. And then let's see. Let's go in descending powers. We have 1/64 y to the 4th. True. Then comes y squared. We have -1/2 y squared. And then moving on to the lower degree, we have negative on the outside, negative of y, and negative times negative is positive 4y to a half, which is the square root of y dy. And the integration is pretty simple, because these are all simple, end up being algebraic expressions. Okay. Now, using the power rule of integration, y to the 4th, integral of that is y to the 5th over 5. 5 times 64 is 320. So that's 1 over 320 y 5th. And then, let's see, next one is going to be y cubed over 3. So 1/6 y cubed, -1/2 y squared, plus y to a half plus 1 makes 3 halves. Flip 3 halves, you get 2/3. That's 8/3 coefficient, y to 3 halves. And then integral runs from 0 to 4. And again, this time the lower limit, 0 for y, makes every one of those 0. That's good. So we're just going to put the upper limit. So like before, let me just substitute these, and then in the interest of time, I'll give you the answer. And there you have it. Here is the answer. So you can follow the arithmetic of what I've done. Again, the answer to this exercise, the volume of solid is 88 pi over 15. And that ends this segment of the exercise. So that was, again, exercise number 38. So we did practice finding volume using discs and washers. So let's now take a look at finding volume by cross sections, and for that we're gonna take a look at these two exercises right here, actually one of them. The question reads, find the volume of the solid with the given base r and indicated shape of every cross section taken perpendicular to the x-axis. We're going to take a look at number 56, this one. So I'm going to copy and paste this one, and then we'll work on this one. Okay, In exercise number 56, here I copied it, so we want to see what the volume of this solid is going to be. So just to kind of make sure I understand it, this would be the radius of that quarter circle, and this is what the solid's gonna, or that cross section is gonna look like. Now the radius is actually this distance, right? That's the radius from here to the point on outside of that parabola. So for example, if I want to know what the radius is, suppose I'm at x equals 3. So this is going to be 3 equals 4 minus y squared. Y is going to be minus 1 here, right? And 3, 1 here. So the radius is actually distance from 3, negative 1 to 3, 1. That's the radius. R is 2. Let's say I'm at the 1 now. At 1 when x is 1. 1 minus 4, 3, square root of 3. Negative root 3 here. And this is 1 root 3. So the radius now is going to be, of course, this is going to be a larger quarter circle. So this one is going to be, and let me make this a little more realistic there. That's how this is going to look like. The radius is going to be from, again, 1 comma negative root 3 to 1 comma 3. That distance is 2 root 3, right? So in each case, it looks like it's going to be double the y value. True? And that's what that is. So I'm going to write the radius then. The radius is going to be 2y of that quarter circle. What is the area as a function of x, therefore? The area as a function of x, it's 1/4, because we're told this is quarter circle. It's 1/4 pi r squared, and the radius again is going to be 2y quantity squared. So that's just going to make it pi y squared. Okay, and we can actually now write this as the volume of the solid is going to be integral, goes from 0 to 4, right? That's from 0. These quarter circles can go from here, 0, and they stop at 4. So it's from 0 to 4 of ax dx, right? Now that's 0 to 4 of, now ax, I haven't actually, I've said x, but I have y here, right? I'll fix that in a moment. In fact, let me do it up here. So x, if x is 4 minus y squared, therefore y squared, I'm down here. So y squared is going to be 4 minus 6. True? And that's pi 4 minus 6. That's area as a function of x now. So it's going to be pi 4 minus x times dx. See how simple that is. The challenge here, when we use this method to construct, not revolve, but to construct a solid, is to be able to find area of a cross section, either as a function of x or y. So something that we just did. Therefore, this is going to be pi. The integral of 4 is going to be 4x. Of x is going to be 1/2 x squared from 0 to 4. And the upper limit, 4 times 4, 16, minus 1/2 of 4 is 4 squared is 16, is 8. 16 minus 8 would be 8. So the area, the volume of that solid is going to be 8 pi. Okay, and there we have it. So we are done with this section. Volume of solids, of revolution, and of course volume by cross section, which involves no revolution. And with that, we're done with this section, with this lecture.